In the meantime, people can join gradually. So welcome all. Welcome to the IOP Online Colloquium. And we are very happy. Today we have with us Professor Francis Halzen. It is almost 10:30 p.m. for him at Madison, and he is in his office, we can see. So we are really grateful to him that he agreed to give a colloquium for us so late in the night. But it is still more in the morning in India. So we are really thankful to him. Professor Francis Halzen doesn't need any introduction, but I can see, there are many young audience. So I will just take a minute to introduce him. So as we all know, he's the principal investigator of the IceCube neutrino experiment at the South Pole. And we are all excited about that. And today he is going to tell us about the fascinating science that we have been doing with IceCube. He is a Vilas research professor and Gregory Breit professor at University of Wisconsin-Madison. As far as his physics interest is concerned, he has been working on several interesting fundamental topics in high energy physics, but mainly his interest lies at the interface of particle physics, astrophysics, and cosmology. Since 1987, he has been working on the IceCube project. The story began with the Amanda experiment, which finally led to the construction of the IceCube experiment, on which he's going to talk about today. And we all know this IceCube is a kilometer cube experiment. So he has shown us that how we can think big and we can travel cosmic distances to catch these mysterious particles, which are coming with energies which are beyond the scope of producing at lab. So this is really fascinating. And he has been a leading scientist in the development of cosmic ray physics and astroparticle physics in 1970. I must say that he has been a constant supporter of our India-based neutrino observatory project. He has helped us on many occasions to come up with a strong physics case for this experiment. And also he has been helping us on several outreach activities related to this project. And he personally thinks that there is a lot of scope for mutual collaboration between IceCube and INO. He has been serving on many advisory committees. He has received several recognitions, medals. If I'll just start naming them, the whole talk will be gone. So just to name a few, recently he received the Homi Bhabha Prize and medal by IOPB, Bruno Rossi Prize from the American Astronomical Society, Pontecorvo Prize, Bulgen Prize, and many more. And just at the end, I would like to mention that I got the opportunity recently to work with him very closely. And my personal experience is that his passion and interest towards science is very infectious. If you will discuss physics with him, you will be really excited to do more and more good work. And he has been inspiring generations after generations to do high quality research through his constant training. And that is the outcome of IceCube family now, where more than 500 scientists under his guidance working to achieve their ambitions and goal in science, in basic science. So with these words, I would like to ask or request Professor Halzen, please take us in the world of IceCube.
Thank you, Sanjib, for this very kind introduction. I will start my lecture, but I would like to say if anyone wants to interrupt me and ask questions, you can do that. I can also answer questions afterwards, even though it's late here. I am more than happy to stay as long as you have questions. So let me you have been looking at my screen. So I'm going to quickly introduce you to the concept of neutrino astronomy. Then I'm going to tell you what IceCube is. Then I'm going to tell you about the cosmic neutrino flux we discovered from the universe. We actually very recently discovered the first sources of neutrinos in the sky. And I will tell you a little bit at the end about what they are. So this is a way to introduce multi-messenger astronomy. So you see, if you look at the top of this PowerPoint, you see that we can look at the sky in different wavelengths of light, and this has been a very successful enterprise. You see, when you look at the sky in microwaves, in optical, in X-rays, in gamma rays, you see totally different universe. And if you look at a particular object, you see different aspects of it. And sometimes you see things in the sky that you never saw before. And the problem is that this game ends somewhere. And it ends, you see, I labeled here all the energies, right? I will try to use as an energy TeV. I'm a particle physicist, so TeV is a natural unit for me. And you see here the energies in electron volt. And we can look into the universe in various, in all this wavelength. But you see there is a demarcation line. This game stops. At some point, you make, of course, if you go to higher and higher energy, smaller and smaller wavelengths, bluer and bluer light, if you want, at some point, the universe just turns dark. And that's what I show here on the right, is terra incognita. We have never seen this universe. And it is like, you know, the dark side of the moon. And so why is this? Well, if you have an object, an accelerator somehow that produces a high energy gamma ray very far away, it has to make its way to our detectors on Earth through the microwave background, 411 photons per cubic centimeter. What's inevitably going to happen at these high energies is that gamma ray is going to interact with microwave photon and make an E plus E minus pair. And that's the end of astronomy. Because once you have a charged particle, the universe is filled with magnetic fields. And, you know, we have magnetic fields in our galaxy. And so these particles will be bent. They will forget their origin before they reach our telescopes. And we are reminded, in fact, of the fact in this picture that in this universe we detect protons and heavier nuclei, but mostly protons. And these protons, they don't tell us where they come from. The sky is totally isotropic, except maybe at the highest energies, but that's a different talk. So anyway, the only way another way to show this is with this picture. This picture I will define this unit. This is new for the astronomers, but what you are looking at is the energy reaching us from the universe in the form of radio waves. That's the left of this plot, in the form of microwave photons here. And then we go through the different wavelengths of light and eventually visible light here, X-rays, gamma rays. But you see, then the flux cuts off. Even the gamma rays don't make it to Earth anymore. They get absorbed in the microwave background. So you can only do astronomy with neutrinos once you reach this energy where the observed gamma rays cut off. And you see here the flux that we discovered. These are a couple of our measurements. I will discuss this in detail. And I will come back to this figure actually later because it's very interesting. So, as I already said, the only way neutrinos reach us from the beginning of time and from the edge of the universe. They are just like photons, they have no charge. They are not absorbed, they don't interact very much. And The only problem with neutrinos is that they're difficult to detect, and we solve that problem. With photons, actually, here, what this figure tells you, this is the cutoff as a function of energy. So here you gradually, when you go to smaller wavelength of photons, higher energy, gamma rays, you lose the universe. And at 1000 TeV or so, we can only see our own galaxy. We don't see the universe anymore. So that's the logic for neutrino astronomy. I mentioned the protons. These protons were discovered, cosmic rays were discovered more than 100 years ago. And we now know that they are accelerated to enormous energies. So I think the interest of a particle physicist in this field is actually this one, I must admit. I remember when a modest experiment in Utah, the fly's eye detector, discovered a particle of 300 million TeV. How can you not spend the rest of your life trying to explain where these particles come from and how it's accelerated? And that's kind of the goal of neutrino astronomy. If you want to realize what challenge this is, Fermi imagined an accelerator covering the circumference of the Earth. Well, in this case, you have to fill the orbit of Mercury with LHC magnets to accelerate that particle. And I don't think that's how it's done. I should at least show once the cosmic ray spectrum. These are cosmic rays reaching in energy from where they are accelerated at the sun with an energy of about 1 GeV to 10 GeV. And then eventually here are the interesting super accelerators that live in our universe that accelerate the particle that I just talked about. Now, if you think a little bit about this problem, it's not just that the accelerator has to produce high energy. The actual luminosity of these accelerators is enormous too. And so there are very few ideas, or there were very few ideas around, there still are, where these particles are accelerated. And I listed here a few: starburst galaxies, gamma ray burst, active galaxies, galaxy clusters. And in the old days, I would go and give you a flavor for how these mechanisms work. Now it's different. I'm going to choose one example, and you will see why I chose this example when we come to the end of my lecture. This is an active galaxy. So what's an active galaxy? An active galaxy is a galaxy like ours. It has a supermassive black hole in the center, 4 million solar masses in our case. But in an active galaxy, unfortunately this doesn't happen in our galaxy, the black hole is cannibalizing its own galaxy. So it's rotating. So as suggested here, you have matter falling in a disk. And when this disk, so the matter piles up close to the black hole, and when this disk, when the particles reach close to the black hole, you have to think of this in terms of general relativity. They meet the rotating frame of the black hole, the black hole winds up the field lines along its rotation axis, and so forms a beam of particles. I'll come back to this picture later. But what do neutrinos have to do with this? Well, a simple picture. I show here the center of the galaxy. If protons are accelerated, this black hole with all this matter and radiation falling in, it's surrounded by light, by radiation of all wavelengths. And so this accelerated proton can interact with a gamma ray in the vicinity of the black hole and produce pions that decay neutrinos. That's the concept of, and now you have a particle then you can track right back to the source, unlike the proton. It's not that different that Fermilab, we have an accelerator, shoot it in a beam, in a target, and neutrinos come out. That's the same here. You have a supermassive black hole that probably accelerate protons in several ways. I'll come back to that. The nearby radiation typically is the most obvious candidate for a target for producing neutrinos. So by P gamma, we produce a neutron and a pi plus, or a proton and a pi zero. So the interesting thing about this 1950s physics, all the physics of this is known, is that there is a pi zero for every pi plus. And what that means is shown in this picture. So the proton interacts with a target photon, it makes a pi zero that decays into two gamma rays. The charged pion decays in the muon and a muon neutrino, and then the muon decays further in a positron, an electron neutrino, and a muon antineutrino. And you see, you count on your fingers, you have a muon neutrino and an anti-muon neutrino for two gamma rays. We cannot tell these two apart, so when we measure a neutrino flux, what it means is that the gamma ray flux is equal to the neutrino flux. The gamma rays have actually higher energy than the neutrinos, but their fluxes are about equal. This is important. For every neutrino you see in this talk, a gamma ray was produced, non-negotiable. This is isospin, or whatever you want to call it. Okay, IceCube. We know how to build a neutrino detector. You need water and photomultiplier tubes. This is the beautiful Super K experiment in the Japanese Alps. The problem is to do neutrino astronomy. This experiment is 10,000 times too small. We didn't actually know this before we built IceCube, but over decades, theorists had kind of agreed on this goal. And fortunately, they were right. So how do you build a detector that's 10,000 times bigger? That idea goes back to Moshe Markov in 1960. And instead of reading what he said, I will show a cartoon. So the way you do neutrino astronomy, you look for neutrinos coming through the Earth. Nothing else comes through the Earth. If you see a particle, you detect a particle coming through your feet, it's a neutrino. This neutrino will fly through your detector. But about 1 in a million times at the energies we are working, it will hit a nucleus in an ice molecule, right, the nucleus, and produce particles. If this is a muon neutrino, among the charged particles that it produced is a muon. And this muon will travel at the speed of light through your detector, even if it's produced outside. In fact, these muons have a range that is from hundreds of meters to tens of kilometers long, depending on the energy. So typically, you can collect these muons from outside your instrumented volume. And it's a telescope because you can tell from the shock wave of light where the muon and the neutrino came from, as shown is in the cartoon. In fact, the speed of light in ice is 3/4 of the speed of light in vacuum. So whereas the muon goes almost at the speed of light, the light goes at 3/4 of the speed of light and stays behind in a shock wave. So you have a detector consisting of light sensors, and if they can map the Cherenkov cone, then you know the direction of the muon. So you use the light produced and detect it with these light sensors and reproduce the direction of the muon and the neutrino. For the theorist, all this is called deep inelastic scattering, and we understand it completely. So the detector completely works by phenomena that are part of the standard model. In the 1980s, physicists tried to construct such a detector of the coast of Hawaii, and that project failed. But unfortunately, around the time they failed, 87, we started thinking about building such an experiment not in water, but in ice. And so where do you find ice? You find ice at the South Pole, but at the South Pole, you also find a runway where the planes land and can bring your detector on top of the ice, and you have the support of a station of the National Science Foundation on the left. On the right, you see the construction of the IceCube project. So for about 10 years, the question is this ice, we realized, and history has shown us right, that it was easier to melt phototubes deep into a glacier than to deploy it in the ocean, where you have to fight the ocean continuously. And so, but we didn't know what the quality of this ice was. We first had to realize that we had to go almost 1.5 kilometers deep to get rid of bubbles in the ice. You cannot build a Cherenkov detector out of bubbles. Your light scatters, and you don't collect this beautiful Cherenkov cone that goes with the muon. And so that was kind of the bad news. We had to drill our equipment deep into the glacier. Here, where my pointer is, you're standing on 3 kilometers of ice. So you can build a kilometer cube detector below 1.4 kilometers, which is what we did. The good news is that we found that this ice is incredibly transparent. In the worst ice in this detector, the absorption length of blue light is 100 meters. You cannot build in a lab a substance that's that transparent. It's 60,000 year frozen snow, which is ultra pure and transparent. So let me come back to this cartoon and now show you a real picture. This is you're looking here at a kilometer cube of ice instrumented by more than 5,000 photomultipliers. In fact, they are deployed on strings, and if you had better resolution, you could see little dots. There are 60 photomultipliers on each string. So they are the size of a basketball, basically. And there are 60 of them instrumented over 1 kilometer, and the top of the detector is at 1.4 kilometers below the geographic South Pole. So here you see a neutrino that somewhere produced a muon neutrino, and the muon goes through the detector, and you see the light sensor slide up. If you see a small dot like that, that means 1 photon was detected. A dot like this, which is close to the track, may be collected a few hundred photons. And so by eye, you can reconstruct the direction of this muon, but by computer, we can do it now to 0.3 degrees. So here, if you didn't get the idea, you see the muon coming in. Red is early, you follow the rainbow, and you see it go at the speed of light through the detector. So this is a picture inside the detector. If this were at all possible, it's of course a cartoon again. And you see these strings, 60 meters long, 1 light sensor every 17 meters. And then you look 125 meters away, and there is another string. And 86 strings fill a volume of ice with more than 5,000 photomultipliers. Of course, this is a photomultiplier on the top right here. It's in a pressure vessel. You will see later why. And it has electronics. What this electronics does, it captures the light and digitizes it. So the whole experiment is digital. The data is collected in the ice, then it's digitized and sent to computers at the surface and then over satellite to the data center where I'm sitting here tonight. So this is an example of what we call a waveform this is a photomultiplier counting light. And each time a photomultiplier has counted detected light like this, it digitizes it, sends the information to computers at the surface. And the computers at the surface collect the information and put it together into neutrino events. So here you see you can only drill holes at the pole in December and January. So this season, the project had deployed 20 strings, and you see the data cables coming up. They will go into this two-story building, and this two-story building standing at the center of the array is just filled with a computer, a cluster that does a first reconstruction of the events, then send that information to Madison, Wisconsin over satellite. What does IceCube see? Well, this is a sad part of the story. If you look up at the sky in neutrinos, you see the atmosphere. Cosmic rays hit the atmosphere, and about 20 kilometers above our heads, they produce pions, and the pions create neutrinos and muons. And we see those at enormous rates. In fact, you collect the neutrinos from all over the globe at the South Pole. And then on top of that, you collect a huge flux of cosmic ray muons that are produced in the sky behind you. So here is a picture of IceCube taking data. So you see what it does is, you see these tracks appearing. And so the computers collect these signals, make them into muon tracks. And then you can see just now the movie repeats. You see this was a big bundle of cosmic ray muons coming from the wrong direction. Of course, we are looking for tracks coming from the bottom. And so this movie you are looking at is 10 milliseconds long. So what that means is that we actually detect 100 billion atmospheric muons every year. We detect 3,000 cosmic ray muons every second. We collect about 100,000 atmospheric neutrinos per year. And we have discovered a cosmic neutrino flux of 200 particles per year. Those are the ones I'm going to talk about. Of course, at this point, I could give you a talk about the atmospheric neutrinos. They are annoying background in this talk, but they also, we have upgraded, they're also an opportunity for science. And we have upgraded part of the detector to transform it in basically a 2 megaton atmospheric neutrino detector. So it's a big India-based neutrino observatory. And you see here a recent result for the atmospheric oscillation parameter. So this the experiment does physics at 1000 TeV, I will talk about, and at 5 GeV. That actually Sanjip is now working with this data, and Sanjip and his group. And so we are going to upgrade this detector even more, but that's a different talk. Now, before I go into the science, let me just anticipate all questions on how you put photomultipliers in ice. The top 100 meters or so is snow. So you just melt the snow. And then you have a hot water drill, and it puts out, in this nozzle here, it puts out hot water under pressure. And so in 2 days, it melts a hole down to 2.5 kilometers, and then you pull the drill out. What you need is a 4.8 megawatt power plant, and you need 200 gallons of boiling water per minute. This whole drill is like a circus train, except it's not on wheels, it's on sleds. This is the drill tower, for instance, here. This is the 2.5 kilometer hose that brings down the hot water to melt the hole. Remember that, imagine there's never a hole, right? We just melt the water, transfer water in ice into water. And we do this using about 40 car wash heaters that are driven by normal generators and normal fuel. So this sounds all very low tech, but it's actually very sophisticated. And, you know, it's an engineering marvel, actually, which I certainly cannot take credit for. Here you see the drill being pulled out of the hole. Ice is an insulator, so it will, this water will remain liquid, sometimes for days. And so you have the time to line up the 60 photomultipliers in their pressure vessels. And so they are ready to be deployed into the now liquid ice. And so you see, this is the cable that brings down the voltage and brings the digital signals back up. And so every 6 you unwind it, every 17 meters you attach a photomultiplier, and then you let the string sink to the bottom, and then it freezes in and you never get your hands on again. It's like a satellite you launch in space. Okay, we built this thing. What did we see? Well, I showed you already this event, which is actually a 2600 TeV neutrino. On the left, you see a different event. You see the movie. You don't see a track. It's actually an electron or a tau neutrino. And so it interacts in the ice, makes a shower of particles, not a muon. And the shower of particles is only about 10 meters long, less actually. And so it's like a point source of light. Remember, this is a kilometer cube detector. So 10 meters is like a point source in this detector. And so, but it gives us another way to reconstruct electrons and taus. They are not as good to do astronomy, but we can do fantastic energy measurement. This is a total absorption calorimeter. So to make a long story short, we operated the detector for 2 years and saw a flux like this. So what you're looking at is the number of events per bin, and the bins are in energy in GeV. So this is 100 GeV, which is the threshold. And then the detector rises above threshold, and around 1 TeV, we see most of the neutrinos. They're all atmospheric, almost all. Then we measure the atmospheric neutrino flux. It's a great opportunity to calibrate the detector. And then you see once, of course, we can also calculate it. And the blue line is the calculation. It's well understood. And you see here, there is a deviation. We see more neutrinos beyond the atmosphere. These reach us from the cosmos. Those are the cosmic neutrinos. So we fit this flux as an atmospheric and a cosmic component. And then you see the cosmic component sets in around 10 to the 5, around 100 TeV. These are 1000 TeV neutrinos, which are called PeV occasionally. So here is the flux. What's the flux? The NDE, look at the top right here. The NDE is the number of particles as a function of their energy. Typically in astronomy, this is a power. Now, EDND is the number of particles, and E squared DND is their energy. So I will always show plots like I already have in the beginning that show the energy of the neutrinos. And so here you measure, here is the energy in neutrinos. These are the measurements from nu E and nu tau starting in the detector. And the blue butterfly, the pink butterfly here, that's the flux we measured on the previous slide by fitting the muon spectrum as atmospheric plus cosmic. You see they perfectly agree. And just to point out, as they reach us from sources far away, they have oscillated into equal flavors of nu e, nu mu, nu tau. They actually decohere, right? They're not oscillating anymore. So that's the result. E to the minus 2.5 is the power. And here you see the same measurements, but now more years of data. And you see the conclusion is still the same. The flux measurement of nu mu's is covers larger energies. The error bars have all become smaller. But we have another check on this figure, and that's this event. This event is labeled a glacial resonance. What is this? Well, this is the glacial resonance. You see the event pictures on the right here. It is an event where an electroneutrino, anti-neutrino actually, for once doesn't interact with the nucleus, but it interacts with an atomic electron in the ice, and it produces a real W, ATGFW, the thing from CERN, that decays into two jets. The lab energy for producing an ATGFW is 6,320 TeV, and that's exactly the energy of the event you see. We see the decay in the two jets in the form of a hadronic component with muons and an electromagnetic component. It's like you are looking at Atlas of CMS, but a much worse detector. But we can do all these things. So there are many signatures that this is indeed an event like that. Now, for this event, we know the cross-section. So as a telescope measures the flux times the cross-section, if you know the cross-section, you can measure the flux from one event, and that's what you saw in this picture. So let me actually show it again. So that event actually is a 5 sigma discovery by itself of cosmic neutrinos, and that's its flux measurement. Okay, so it's of course a wonderful check that we measure the energy correctly. So back to this. Where do these neutrinos here in the tail come from? Well, I can plot them on a map. This is a map, a projection of the universe with the galactic plane on the major axis. And so the pink events are nu e, nu tau reconstructed with modest resolution. The little red dots here, those are the muon neutrinos reconstructed with better resolution. The first thing is, if you look at the neutrino sky, you don't see the galactic plane. This was a real surprise, because whatever you are observing, you're first supposed to see the sources in your own galaxy, which are nearby, and then the same sources in other galaxies further away. So you can actually, we actually did observe the galaxy. We actually observed the galaxy. If you look at the bottom here, this is the galaxy in gamma rays. And in gamma rays, you see the galactic plane, and then you see the sources in other galaxies far away. We don't see that. And we see the same flux actually as Fermi. But we see a flux from other galaxies that's much larger than the flux Fermi sees. In fact, if you went out and you had neutrino skies, you would just see a sliver of 10%. The flux on the galactic plane only contributes like between 9 and 30% of the total cosmic ray flux in the map. So everything we see actually, oh, next question. Where are these gamma rays? And I will go to this very quickly. I told you for every neutrino, I've shown you many by now, there is a gamma ray with actually higher energy, but they're one-to-one. So these gamma rays are absorbed, but I didn't finish the story. Of course, these electron-positron pairs are going to radiate. The photon is going to pair produce again. So you form a shower in the microwave background, And the shower, if you have a PV photon accompanying a PV neutrino, it will actually arrive at Earth as many 10 GeV gamma rays. And we have a beautiful instrument called Fermi. It's a pair spectrometer flying above the atmosphere, and it can detect these photons. And so now I'm coming back to this picture, and I make this discussion short, but you see here, this is where the universe turned off. So the actual flux, this is the power seen by Fermi. You see the flux I just introduced to you is larger than the gamma ray flux. So this was a total surprise. So we actually, the energy in this extreme universe, in neutrinos and in protons that produce the neutrinos, is larger than the flux in electrons that produce the gamma rays. So this extreme universe of cosmic accelerators is a world, a universe of protons and neutrinos. And so you'll need neutrino astronomy to figure out what's happening there. So if you don't buy this argument, I can make this argument in a much more careful way, and you can ask me later, but in the benefit of time, I'll skip this. So, as I said, all observation were surprises. We see the universe, we don't see our own galaxy, we see it now at the 10% level, but our galaxy is a neutrino desert. There are sources of neutrinos in other galaxies that don't exist in our galaxy. And I'll make an educated guess. We don't have an active black hole. And I'll come back to active black holes next. So the first sources. Why do you find the first sources? We have been operating this detector for 10 years. Why do we find them now? Well, we find them now because we went to this program that I won't discuss. We recalibrate the detector, analyze the data, calibrating and using every individual optical module. All our analyses were already using neural nets, but we moved to the much more modern machine learning techniques. And we stopped approximating the pointing of the neutrinos by Gaussians, which you can do in astronomy with regular telescopes, but doesn't work in neutrinos. This is a highly technical story I will not go into, but you heard me talk about 3 major improvements. So then we went back to our 10 years of data. So to give you a feeling, this is a year of data of IceCube. There are 138,322 atmospheric neutrinos. The purity of this sample, actually neutrinos, is 97%. And so we have 10 years of data like that, which I cannot show superimposed with PowerPoint. In this map, there are 200 cosmic neutrinos. Remember the flux, we know our detector, we know the flux, we know we see 200 cosmic neutrinos. 12 of these are actually nicely separated, just like this Glasgow event from the background, and you can point your finger and say, this is a cosmic neutrino. So we are going to search this map for neutrino sources. So I show you here a blow up of a little piece of the map, 6 degrees by 6 degrees. And you see these are the neutrinos, and you see the colored red points, that's a source, which I will talk about later. But notice, if I don't color the points, you don't see them. You don't see the source. So we have something called the maximum likelihood technique, which I won't explain, but what it does is it searches every point in the map for a clustering of neutrinos that have on average higher energy and stand out from the uniform atmospheric background. So you look for points where more neutrinos are produced than average and they have higher energy than average. So this would then be candidate cosmic neutrino sources. If you do this, you search this source, the highest p-value, the hottest source is this one. And it's very close to a nearby active galaxy, NGC 1068. I will spare you the details because we also find this source in a different way. We have a list of 110 sources pre-selected, of course not selected after the fact, where we go and point the telescope. I mean, we point the analysis. And so we look in the direction of these 110 sources, and the strongest source is again this active galaxy NGC 1068. It's actually offset, our cluster is offset by 0.11 degrees from the real astronomical position. We see 80 events in this picture from this source, and the probability that of this excess is 5.2 sigma. Now, we can do better than this. This maximum likelihood method allows you actually to compute exactly what your trials are and determine a mathematically defined p-value that this source is not accidental. And so this source will appear accidentally less than 1 in 100,000 times in your data. And so that's well above 4 sigma as well. So there's no doubt this source is real. So we can now make a picture like astronomers make. This is the direction, 0 here is the direction of the source. You see here the atmospheric neutrino background, and here you see the signal. And the signal is exactly as the profile that we expect from the simulation of the detector. This is what a telescope with 0.3 degree angular resolution is supposed to produce, and that's exactly what we see. So we see again, there are 17, so like 40 events on a background of 40. Now we can ask the question, are there other sources? I've only looked at the strongest one. And then we do a binomial analysis and ask, what's the strongest source? That I just explained. What are the 2 strongest sources? If I only choose 2, which is the next one? And if I choose 3, which is the next one? And so this way we discovered TXS 0506 plus 056 and PKS 1424 plus 240. These are again active galaxies. All these sources have active black hole at their center and produce the neutrinos. We can even go further, and we have another 3 or 4 sources. I like to show NGC 4151, and because NGC 1068 and 4151 were the first 2 active galaxies discovered by Seifert in 1943. So here we are, you know, some 80 years later, discovering the same sources in neutrinos. Now, this source, TXS 0506, we knew about already. We had already nailed it in 2017. And we did that by what we call a multi-messenger campaign. Just quickly, as soon as we detect a neutrino, the computers at the surface reconstruct the direction, and this direction is sent over Iridium satellite to all astronomers in the world who want to point their telescope in the direction of where this neutrino came from. So we go from light in the ice to the astronomers pointing a telescope, less than 1 minute. So this is what a telegram looked like. It gives the coordinates, and now it also gives the energy. And then later we use better reconstructions and send a second telegram updating the direction. This is a neutrino we discovered in 2017, September 9, and it's a 290 TeV neutrino, and it came right from the direction of the source TXS0506, which we now found again in the analysis of our 10-year map. Same source, it's actually only second. But so you see here the two reconstructions and the source. And in fact, this source was flaring, which is very unusual. And also it was emitting TeV gamma rays, which is also unusual. And so this builds up to something like a 3 sigma effect. It's evidence, not discovery. However, so first, at some point, we had no idea whether anyone looked at our telegrams, but at some point, more than 20 telescopes were looking at this source. And there was actually an optical telescope, MASTER, a robotic optical telescope, who was looking at this source 73 seconds after the light was in the ice. So we published this multi-messenger campaign with 3 sigma evidence, but don't forget to read the second paper that goes with it. We looked at our data, 10 years of data, and what I've been talking about is this little blip here. That's the 290 TeV neutrino. This is what we saw in 2014. We knew about this, but couldn't claim it until we had a real direction to look at it. In fact, published in a thesis, the University of Geneva. So this was a 100-day flare in neutrinos. We had enough events to measure a spectrum, something like 12 events, e to the minus 2.2. And the neutrino flux is at the Eddington limit. And if you don't know what this is how large it can get. And so the other thing is, there are no gamma rays. There's no gamma ray flare. No, the gamma rays are missing. Remember that. The gamma rays are already subdominant in our diffuse flux. When you look at the galaxy, the energy is the extragalactic universe at the highest energies. We mostly see neutrinos. Here again, we only see neutrinos. There are practically no gamma rays. Now here, this optical telescope did something very interesting. It was looking at the source. So you see here, the 17 event in neutrinos, in gamma rays. In radio, actually, the source was flaring, but it saw a change in signal to noise in optical light of a factor 50. And it had never seen such a thing before. It had been looking at the source since 2006. But then 2 hours after the neutrino, it suddenly did something with a signal to noise of 50. And to make sure they understood their telescope, and this cannot happen accidentally, they looked at the source for 2 more years and then published. You see, it didn't do anything afterwards either. This is a discovery of, way beyond 5 sigma by the optical experiment by itself. Okay, so this is my conclusion. We have now 2 sources, TXS and NGC, and then evidence for a handful more, which I won't discuss. I'm going to use the few minutes I've left to tell you what we think we discovered. But so, the question I always have is this the first step to solving the cosmic ray problem? Maybe, maybe not. But I remind you of this picture. And so you have matter falling in a disk. It's like, you know, the water swirling into out of the bathtub, so the black hole cannibalizing this, and it makes this jet. This jet we think is irrelevant to the story. What's relevant is the region at the center near the black hole. So in an active galaxy, what do the astronomers tell us about the vicinity of the black hole in an active galaxy? Well, you see here a blow up, you see the accretion disk, the black hole, but you see this fog here. That's what astronomers call the corona. So this corona is surrounding the black hole. Well, we are not sure what the geometry is, but I'll assume that it's just surrounding the black hole. And it's dense. It's opaque to gamma rays. It's a big ball of X-rays, which the astronomers measure and can tell us how many there are. But it's also, there's so much matter accumulated there. There are so many protons that you can make neutrinos both by accelerator interacting with the X-rays or the accelerator interacting with the protons, which astronomers call hydrogen. Okay, so a bit more detail. So remember, Fermilab, you need an accelerator and a target. Where is the accelerator? Well, in the accretion disk, there are turbulent, high and turbulent magnetic fields. And there are ways to accelerate protons in the accretion disk. Then when the protons actually fall and start moving towards the black hole, you can form shocks and you can accelerate particles. There are probably high energy winds blowing off this black hole. So there are many ways to accelerate protons. So there, in fact, there is a matter of choices, with at the moment astrophysicists giving preference to acceleration in the accretion disk. What is the target? I already told you, there is a big ball there, this corona, thick in photons and thick in protons. And so if you have accelerated protons anywhere in this vicinity, it can interact with this target and produce neutrinos. What do we actually see? I didn't show you neither this is the flux of NGC 1068. It's again the energy, and you see here the energy in GeV. So our signal starts around the TeV and goes about up to 100 TeV. So this is what we measure with all the errors, systematic and statistical. Remember, 40 events on a background of 40. There are two models which are consistent with the story I'm telling you. But what I want to draw your attention to is this. There are no gamma rays, just like with TXS, there are no gamma rays. So where are the gamma rays that by isospin or whatever you call it have to accompany the neutrinos? And remember, this is a logarithmic plot. So the suppression here is 2 orders of magnitude. There are really no gamma rays. But it's inevitable that you did produce gamma rays when you produced the neutrinos. In fact, there are gamma rays at low energy, but these come from somewhere else. We think we know where they come from. So here is the answer. So you can do a simple dimensional analysis. Sorry for showing an equation. So think of this as a target of size r of X-rays and protons. In fact, the optical depth of this corona is larger than 1 in both protons and in X-rays. And so the neutrinos, of course, don't care. You produce them on this beautiful target that has a thick optical depth and allows you for two mechanisms. But the gamma rays, the optical depth for gamma rays is the gamma-gamma cross-section times the density of target particles. Remember, the opacity is the cross-section times the density of target particles. The density of target particles is measured by the astronomers. So this is the number of X-rays I have to stick in this corona. And of course, when I make my corona smaller and larger, then the density will increase and decrease. So the capability of absorbing gamma rays depends on the size of this corona. So I can transform the neutrino flux we see, which is equal to the number of gammas we see. I can transform into this radius. I can calculate the radius. And the radius turns out to be 10 Schwarzschild radii. Now, for those of you who are not experts, what's a Schwarzschild radius? This is 1.5 Schwarzschild radius. You all remember, I guess, the picture of the M87 black hole. So our neutrinos, and that's confirmed by modeling, I just did dimensional analysis, models confirm this, are produced like at 10 Schwarzschild radii. This is a place where telescopes can only reach when they do what these telescopes did, that is, make an interferometric radio picture of, by combining radio telescopes observing in unison all over the Earth. There is actually already a proposal to image NGC 1068, from which we discovered the neutrinos. So, end of the story is, did we discover the source of the cosmic rays? They come from this dense region close to the black hole. It's almost something that we should have guessed, but then we guessed many things. But now the data is certainly steering us there. Well, of course, it's too soon to tell. These stories in astronomy always get gradually more complicated. But at the moment, this is kind of the story of neutrinos. The good news is that finally, after 100 years, and that's my last conclusion here, I have the feeling, and I hope to have convinced you, that we are closing in on the sources of the cosmic rays. We have the means, the methods, the tools with multi-messenger astronomy and by ourselves. The most important thing we showed in the last 10 years is that actually with a kilometer cube telescope, you can do astronomy. And the other thing that you should have learned from this lecture, I hope, is that we need more neutrinos, we need neutrinos with better resolution, we need more telescopes. And this is happening as well. As I speak, there are telescopes are being built in Lake Baikal in Russia and in the Mediterranean Sea, and which will eventually have the size of IceCube, so will be 3 kilometer cube. Then there are initiatives in the Pacific, one off the coast of Vancouver, which is called P1, and then there are 2 very ambitious projects in China. And they are going to build something 10 times bigger than IceCube. And that's also what we are planning to do. We are about to finish the technical design of a next generation detector, which will have 8.5 times, almost 10 times the volume of IceCube. And this project was already very positively reviewed by the Decadal Review in the US, so we hope to succeed. And that's the end of my story. These are my collaborators, and that's during COVID. These are my collaborators before COVID. I have no picture after COVID, but these are all the young people that did the beautiful work that I described tonight. Thank you.
Thanks a lot, Professor Halzen, for your comprehensive talk and starting from the source, then the detection, and then the outcome. So now the floor is open for questions. So if there are questions, please, you can raise your hand or just speak.
Hi, sir. I have a question.
Yeah. So, sir, I think Ashish is a postdoc in our group at IOP. So Ashish, go ahead.
Yeah, thank you, Francis, for the nice talk. While mentioning about the black hole at the center of Milky Way, you said that Milky Way is a neutrino desert, and we don't see anything coming from the center of our galaxy. Even though
Yeah,
it's not an active nuclei, we should still expect neutrinos from Hawking radiation from the center. And are those like within the reach of IceCube?
no. Um, no, these are these supermassive black holes. Of course, there is Hawking radiation, but it's not detectable. We have ways to look for Hawking radiation, and we look for Hawking radiation from primordial black holes. But for the supermassive black holes, you know, imagine the picture I described. You know, this black hole is a mess. It's surrounded by all this stuff that didn't make its way in, and so the Hawking radiation is totally overwhelmed by this, and so the only chance for us to detect Hawking radiation is if there are black holes, primordial black holes formed, for instance, at the end of inflation or in the early universe, and they get a certain size, they will explode. I've forgotten, it's like 10 to the 17 grams or so. And so those emit neutrinos among the Hawking radiation. And we have actually looked for these, although not recently. I remember writing papers on this during the days of Amanda.
Yeah, I actually have seen your paper on that, but
yeah, and also there is an analysis. Sorry, there is an analysis going on right now by one of our collaborators at Georgia Tech.
Okay.
Yeah.
There's one more question I have, which is actually quite unrelated. While drilling, did IceCube see anything of importance to glaciology or geology? And
oh yeah, we have written a lot of glaciology papers, and I think that even 1 year in my life I wrote more glaciology papers than particle physics papers. I know we can check that, but so basically everything that we discovered was a surprise in glaciology as well as in astronomy. That in astronomy, if you do something new, there are always surprises. In glaciology, there's not supposed to be surprises. You are supposed to understand. So to make it a long story short, bubbles. There was bubbles were supposed to disappear at 400 meters under pressure. Well, they didn't. See, we deployed strings, actually, photomultipliers at 1 kilometer depth. And the scattering length on bubbles was 40 centimeters. So the ice was, and the glaciologists had a debate whether these bubbles, at shallow depths above 400 meters, you see in the ice cores, there are bubbles. And there was a debate whether they actually disappear under pressure. And this debate was unresolved, and we resolved it. Now, the absorption length of light in ice, that was totally unanticipated. There were papers that measured the absorption length of light in ice in tabletop experiments. And they got answers like 8 meters. I think there was nothing wrong with these experiments, but you know, with a tabletop experiment, you cannot measure a quantity that's actually 100 meters. And so, you know, that was again a total surprise. Now, we actually have a method where we measure the dust in the ice. And with that method, we can actually see volcanoes that you cannot see in ice cores. So I won't describe it here. So, but yes, I mean, this is, and also nobody has ever instrumented a glacier with a 1 kilometer cube measuring equipment. So we have actually proven that in the last 10 years or so, this glacier has not deformed. It has, the South Pole is a glacier that runs off the West Antarctic mountains. But it glides over water at the bottom of the rock, at the bedrock.
Okay.
And so we have inclinometers in one string, in every module. And so again, with the upgrade that's coming up in a few years, we're going to do a lot of glaciology. Yeah, this has been an instrument that has contributed to glaciology. I can say this in a modest way, I think.
Okay.
So, sir, in this context, this finding of dust layer, was it a surprise or like?
Yeah, the dust layer, of course, there are many dust layers. That we had the idea that the ice would get better if you go down.
Right.
But yeah, we ran into this dust layer. But once you know that it's there, you can take care of it, right? Right. With ice, it doesn't really matter what the scattering or absorption is. If you understand it, and you can use it to reconstruct the propagation of your photons in the ice, that's all that's required. You don't care what the optics of the ice is, you must understand it. And then implement it in the reconstruction of the light propagating through the detector.
So the plan, when the proposed plan of expanding the detector, since it's a cube, so it will be expanded equally in all the dimension.
Yeah, these layers, there are no surprises anymore now.
Okay.
The ice is, the ice is in the center. So it snows on Antarctica and it keeps snowing. And so the layers are compressed gradually. And so the layers of ice are about compacted snow. In the center of the detector, it's like 70,000-year-old snow. And there was no pollution in the atmosphere then. And the purity of this snow is infinite, right? And so it's the absorption line, basically. Yeah.
So we can also go deeper with time, right? We can also put the strings more deep.
Yeah, I mean, the next detector strings are going deeper. I've forgotten by another 100 meters or so. Okay. There is another 450 meters between IceCube and the bedrock. And the ice is getting better and better as you go deeper. So, but expanding in the horizontal direction, which is what we mostly do, there will be no surprise. These layers are, they actually, the Russians have a station at Vostok, which is like 1,000 miles away, and they see exactly the same layers.
Okay.
They have taken cores, and they see exactly the layers we do. Yeah, that's a story that we don't talk about anymore. This was exciting during the Amanda days. It took us 10 years to understand the ice. And so it was not easy. And I always tell glaciologists, we are not smarter than you. We spend more money and effort. But now I think there are no surprises anymore.
So we have a question from Anil. He is from Daisy. Earlier, he was a student in our group. So yes, Anil, go ahead.
I met Anil in Aachen.
Yeah, hello Francis. Yeah, so I have few questions. So maybe first regarding ice. So I heard that the ice, the glacier, it flows. How does it can give problems to IceCube operations or something?
Nothing. I mean, we put strings in the first strings we put in, I think, was in 1994. So that's almost 30 years ago, right? And we're doing this right. So these strings have moved by 300 meters. But the whole detector moves uniformly. It's a glacier, and it moves, it just translates. It doesn't deform or anything. In fact, this was a big question from the glaciologist. And that's why we have these inclinometers to see if the strings tilt or warp, or the strings don't do anything. They just move and keep moving away from Arctic mountains.
Okay. Yeah. So my another question is regarding, let's say if supernova occurs, so will IceCube see some signals like in what energy ranges, if possible?
Oh yeah, I mean, if there is a supernova anywhere in our galaxy, we'll get well over 5 sigma signal. In fact, and we also collect a supernova signal in a very different way. We, an experiment like Super K, which I showed, they will collect, say, from the center of the galaxy, few thousand neutrinos, right? We will collect more than 1 million, but it's very different. Their neutrinos, they can reconstruct, they can show you a picture of it, they can measure the energy. What we do, we get these 1 million events in 3 seconds, and we know when every photon arrives. So we make a very detailed movie of the supernova with higher statistics than Super K. But we cannot tell the energy, we only can tell time. We can also tell the energy, but not as well as Super K. So it's a totally different way of detecting the supernova. And so it will be fantastic to have these complementary measurements between the two detectors. I mean, if you compare that with seeing 21 events in 1987, it's going to be incredible.
Okay. Yeah, thanks. I have one more question. This is regarding, let's say, this cosmic, if you talk about cosmic rays or cosmic neutrinos, they achieve energy of, let's say, TeV, PeV ranges. I mean, how does such a large energy they get? I mean, because just by annihilation of particles, it may be difficult. So it must be some kind of electromagnetic way to do this energy.
No, I mean, okay. I mentioned all the possibilities at near the center of the black hole to accelerate particles. So the most conventional idea is that the particles falling in the black hole, the material, get shocked. And at the shocks, you can get acceleration. We know that since Fermi, right? So that's one example. On the accretion disk, you have these fluctuating fields, and there they actually think it's by magnetic reconnection that you accelerate the particles, not by shocks. But yeah, I mean, there is a whole community worrying about that, and I didn't discuss anything. I didn't discuss the acceleration. I just pointed at the possibilities. But
Okay.
the standard assumption still that these particles are accelerated somewhere in shocks, which is the old Fermi idea.
Thank you.
Can you ask a question, Sanjeev? Hello? Sanjeev, can I ask a question?
Francis, so Professor Ajit Srivastava,
Yeah,
he's from our institute.
Go ahead.
Thank you, Professor Halzen. A very beautiful talk. One question is about the acceleration mechanism itself. If these black holes are rapidly rotating, then is there a possibility of a Penrose process being responsible for the acceleration?
Well, it depends what you call the Penrose process. I think, you know, the jet is kind of, we don't understand the jet. So I could tell you that's a possibility that it's relevant there. But no, I don't think anyone has speculated on that mechanism, accelerating particles. My feeling is that it's very much a general relativity, pure electromagnetism mechanism that's responsible.
Okay, thank you. One more question about this ice, clarity of ice. One normally expects cracks in ice. Is one? I mean, are we clear that there are no cracks in this IceCube detector in the interior?
We would know if there were. You know, I won't go to my backup slides, but as I just mentioned to Sanjeev, we have spent 10 years to understand that ice.
Okay.
In fact, and so I think we now understand it in such detail that, you know, like it's like asking the atlas of CMS detector where there's a crack in it. There isn't, right? They would notice immediately. That's my answer for the ice. We really have understand this ice in minute detail. And so, you know, the reconstruction of, actually the reconstruction of the neutrinos, of course, afterwards gives us a lot of confidence. We made models we understood the optics of the ice so well at the end of Amanda that we didn't have the computer power to use the image, the model of the ice to reconstruct neutrinos. We just didn't have the computers. That's finished now. We understand the ice in much more detail, but there are much better computers now, so we can reconstruct. But so you know, we have something like a crack in the ice would really stand out in your data.
I mean, that it still seems very surprising to have such large freezing of water, such large crystal in some sense, which is defect-free.
I mean,
a defect-free region. It's already very remarkable result, I think.
Okay, so there are many things. I mean, what would happen to it? You know, there is the only thing that actually happens is that it's floating on the bedrock, and so the layers are a little bit warped following the bedrock.
Okay.
But this is a very gentle process, and that's the most extreme thing that ever happened to this ice. We didn't know that when we started many years ago, but at the boundary between the ice and the bedrock, the temperature is 0 degrees C. So there are, you know, there are lakes under Antarctic ice. And so these lakes are connected with rivers. So it's like a hydraulic network on which this glacier is floating. Okay. And so nothing abrupt happens to it. In fact, we can see the deformation of the layers connected with the bottom of with the bedrock under the glacier. But it doesn't do anything violent like producing cracks or so.
Okay, thank you. Yeah.
And it gets condensed and packed very gradually, right? It takes thousands of years.
Okay, thank you. Yeah.
Sanjip, are you muted?
Yeah. So okay.
Ah,
So
okay.
I'm asking if there are other questions
Oh, okay.
from anybody. If there are other questions, we can still take questions. Francis gave me the liberty that it is midnight and he's in his office. Then he needs to drive back, but he's happy to answer. So if you have any questions.
You can also email me.
Right. So then feel free. So I don't see any hands. Anil, is there anything in the chat?
If you
No, not yet.
no. So if you think of any urgent or not so urgent questions later, just send me an email. I'll answer it.
So Francis, before we wrap up, just one thing. So you mentioned what I believe before 2012, like when you announced that we have seen what we wanted to see, but before that, the detector started seeing the atmospheric neutrino events, right?
Yeah.
And so it is like, when you do a calibration, when you make a detector in your lab, right? You put artificial sources and you calibrate your detector.
Absolutely.
Yeah. So I believe the whole idea going to South Pole, drilling the ice, putting that whole machinery, and it will be able to give you the charge particle track, and then you reconstruct their energy, angular resolution. So I think just a comment, like when you see the atmospheric events, you know that I'm in the game, right? The whole concept works, right?
Absolutely. And in fact, on this, I always, people often ask me, were you most excited about? And my answer is always the same. It's when we saw atmospheric neutrinos. That happened, I think, in 96 or 97. And that's when we knew the methods worked, right?
Right.
Because this, ice may not have been the right material for a Cherenkov detector. We didn't know. So it was a big gamble, a risk. And the flux may have been smaller than it is. I think I tried to explain that the flux actually by theoretical concepts that we see is very large, right? We didn't expect to see cosmic neutrinos after 2 years. Our goal was always at least 5 years of data. But fortunately, we were lucky.
Right. So, so I think seeing that
the atmospheric neutrinos, without atmospheric neutrinos to calibrate the detector, I think it would be very, very difficult. I don't know if you could do it.
And another thing you mentioned, like when you compare always with a beam experiment, so we are also kind of seeing a neutrino beam, but very extraordinary in nature, right? With our detector, right? So it is kind of like a long baseline experiment, but in a different nature, right? We are seeing the beam of neutrinos.
Yeah, that's true.
And
mean, especially when you see neutrinos from point sources, it's like seeing a beam, right?
And in the long baseline experiment, there's a concept of near detector and far detector. So I think we also have that, like, when you see the events from the top, basically, then you can think of it as like a near detector. And then, when you see the things from coming through the earth, it's like a far detector kind of, right?
Yeah. In fact, in the beginning of Amanda, we learned there was an air shower array at the top of the experiment. It was an air shower array built by Alan Watson from Leeds, which was called Space. And we learned a lot about ice by doing coincidence between Space and Amanda, which we are still now doing with IceStop and IceCube, right?
Right. Great. So, Francis, any last word from you for young people in the audience?
Thank you very much for your attention. And it was a pleasure to make this presentation.
I know we are really glad and thankful that you spare your time, and it is already midnight and you are in office giving us a colloquium for Indian time, like it is in the morning. So we are really grateful, Francis, and we are excited, with the IceCube science. And you mentioned about many neutrino telescopes have been proposed. You are in the committee's advisory board. So are they going to bring something new on the plate, or they are just the replica of what IceCube is just doing or is planning to do? Like any complementarity?
I think that's not a question to answer. We are doing astronomy, right? It's not like a particle physics where you look for the Higgs and you find it or not, right? The sky is big. There's a lot happening.
Okay.
So telescopes that's how astronomy works, right? God knows how many 4 or 5 meter telescopes there are. They all do something interesting and different. Of course, the highest priority, of course, and this has kind of already happened, Baikal has confirmed our flux at the 3 sigma level. Right. And I guess the Mediterranean detector will do so soon as well. And so, but then, they can go out and discover something that we haven't thought about.
Yeah. Mm-hmm. And their locations are also like important, where you are building on the globe.
Yeah, actually, if all the telescopes are built that I mentioned at the end of my talk, we can see the whole universe all the time.
Oh, okay.
Right.
That is okay. Thank you, Francis, for this exciting talk. And I think definitely, your slides will be available and students will take a look. And if they have queries or questions, they will get back to you. And anyway, I think we all have your book that we all started with, your particle physics book. So thanks again, for all these exciting sharing of knowledge. Thank you, Francis, and good night. Drive safely. It's already midnight.
Thank you.
Thank you.
Okay. Bye.
Bye.
Bye.